Have you ever wondered how a seemingly passive panel on a rooftop can harness the power of the sun and turn it into usable energy for your home or devices? It is a remarkable process that relies on fundamental principles of physics and semiconductor materials. The core mechanism by which light absorption generates electricity in solar cells involves photons, the tiny packets of light energy striking a semiconductor material, typically silicon. When these photons are absorbed, they excite electrons within the material, freeing them from their atomic bonds and initiating an electrical current. This phenomenon is rooted in the unique properties of a p-n junction, which is formed by joining p-type and n-type semiconductor materials. The p-type material has an excess of positively charged holes, while the n-type material has an excess of negatively charged electrons. At their interface, a depletion region forms with a built-in electric field. When a photon with sufficient energy strikes the semiconductor, it transfers its energy to an electron, allowing it to jump across the band gap. This creates a free electron and a corresponding hole. The built-in electric field then acts like a miniature conveyor belt, sweeping the free electrons to the n side and the holes to the p side, thereby creating a voltage across the junction. Understanding this process allows engineers to design solar cells that maximize efficiency and power output. By carefully controlling the doping levels in the p and n regions and optimizing the thickness and composition of the semiconductor layers, we can enhance the absorption of different wavelengths of light. Furthermore, texturing the surface of the cell helps to trap more incoming photons, ensuring they have a greater chance to be absorbed rather than reflected. Attaching electrical contacts to both sides of the p-n junction then enables the collection of the separated charge carriers, converting this internal voltage into an external electrical current. The efficiency of this conversion depends on several factors, including the semiconductor's bandgap energy, which determines the range of light wavelengths it can absorb, and the lifetime of the charge carriers before they recombine. Advanced solar cell designs, such as tandem cells, overcome the single bandgap limitation by stacking multiple layers of different semiconductor materials, each optimized to absorb a specific part of the solar spectrum. This allows for a much broader capture of the sun's energy, pushing the boundaries of solar energy conversion. Ultimately, the efficient conversion of sunlight into electricity in a solar cell boils down to the intelligent engineering of semiconductor junctions. By understanding how light interacts with matter at a quantum level and harnessing the internal electric field of a p-n junction, we can continuously refine the technology to capture more of the sun's abundant energy and power our world sustainably.